All right, example 404 says find the eigenvalues and eigenvectors for this matrix. Now, conceptually, this isn't difficult to do. You just do 4 minus, well, you subtract lambda on the main diagonal. But then we'll have to find the determinant of this thing. And the lack of zeros in this matrix is going to make that not fun. Of course, we could do this and take the determinant of it using that technique. And that would certainly work, but I want to use this as an opportunity to show you how to get Octave to do eigenvalues and eigenvectors for you. Well, eigenvalues anyway. So let me turn on Octave. Here's our matrix, and I've got that in here as M4, I believe. Let's see this. Yeah, those match. So if you just type in eig M4, that will give you the eigenvalues. And Octave and MATLAB, which it's based on, do everything numerically, and so they give it to us in complex form. But this gives us one eigenvalue is 8. The other eigenvalue is 3, and its multiplicity is 2. All right. So the question is, could Octave go ahead and give us the eigenvectors as well? The answer to that is yes, but I don't want to use it because it's going to give us some ugly information. This is M4. If you put in an AB like that to begin with, this will give you the eigenvalues and eigenvectors. The eigenvalues are given to you down here. As this diagonal matrix, it puts an eigenvalue, it puts the eigenvalues along the main diagonal, and up here it gives you the eigenvectors that go with them. Let's see, this first column I believe it's done column by column. So this would be eigenvector that goes with 1. Notice some of these eigenvectors wind up being complex. So anyway, it can do it, but it also does things like normalizing them, making them have length 1. So these numbers are pretty hideous. So I don't want to use, I want to use Octave here to get the eigenvalues, but let's do the eigenvectors manually. Okay, so first up, let's do lambda 1 equals 8. So I'm going to subtract that off of my main diagonal. So I get 4 minus 8 is negative 4. 1 minus 8 is negative 7. 9 minus 8 is 1. Then 2, 3, negative 1, negative 3, 2, 4. And that's the worst looking matrix I've ever written. That's probably not true, but it's definitely up there. All right, so let's type that into Octave. And I think I'm going to want to tone Octave down a little bit. Nah, there's plenty of room to see it. Well, let's see. Let's call this M. We have minus 4, 2, 3, 0, negative 1, negative 7, negative 3, 0, and 2, 4, 1, 0. Okay, this was for 8, so we're expecting to have only one free variable here. And sure enough, we do. Let's see, what is this? We've got 1, 0, minus a half, 0. 0, 1, positive a half, 0, and then a row of all zeros. All right. So x, y, z. This is going to, we'll see, z is free. So the top row gives me the equation x equals 1/2 z. Middle gives me y equals negative 1/2 z. And z is just z. So I'm going to go ahead and just pull these. I'm going to go ahead and just pull these out as my vector. So the basis of the eigenspace is 1/2, -1/2, 1, or let's get in the habit of writing these without fractions if possible. So I'm going to multiply all that by 2 to clear out those halves. So this will be 1, -1, 2. Both of those are correct, but I'm circling the one that I think looks nicer. Okay, so that's for the first eigenvalue. For the second one, now lambda 2 had a multiplicity of 3, so we might wind up getting two free variables, and therefore a two-dimensional eigenspace. But we might not. We won't know until we work this out. So let's see, I've got to subtract the 3 off of my main diagonal. So I'm going to get 1, -2, 6. And the rest of it stays the same. Now row reduce this. All right. Oh yeah, I can look at this and tell it's going to have two free variables because all of the rows are multiples of each other. So you get that, you reduce it, and yeah, you get 1, 2, 3, and then zeros everywhere else. Didn't really need octave for that. I just sort of went on octave autopilot there. Yeah, 1, 2, 3, 0, and then a bunch of zeros. And so this is going to give me, let's see, x, y, z. Y and z are both free. So this top line gives me x equals -2y minus 3z. Y is just y. Z is just z. So let's go in and write this stuff. This is 1y plus 0z. This is 0y plus 1z. And I can pull my vectors out of here just from looking at these coefficients. When you do that, be sure to get the negatives with them. So a basis of this eigenspace has two vectors in it, -2, 1, 0, and -3, 0, 1. All right, and with that, we're done with this example, but I like to play with these things, so I'm going to play with it for a minute with octave. Let's see, this matrix, I think it's called M4. Yeah, there it is, M4. First up, before we do that, let's look at this. What's it? Oh, these are supposed to be brackets. All right. So if we look at that, if we look at our eigenvectors that MATLAB, that Octave gives us, we've got -2, 1, 0. Huh, that doesn't look at all like what they have. Oh well, let's don't worry with that. Let's just look at putting in my two, I'm going to call these A and B. A is -2, 1, 0. B is -3, 0, 1. All right, so if I take M4 and I multiply it by B, what was the eigenvalue here? The eigenvalue we were dealing with was 3. So if I multiply this out, it should give me negative 903. And same for A. If I take A and multiply it by M4, it should give me negative 630. And any linear combination we want. Say, I'll just pick a number, say negative 2A plus 5 times B is that. Well, if I take M4 and multiply it by this, it should give me 3 times that. So it should be negative 33, negative 6, 15. And sure enough, it is. All right, so that's it for this example.